Okay. Last lecture we have proved theorem related to parametric differentiation. X was defined by letter f of t. X was function of t. Y was another function of t, and it was given that f dash exists and is continuous. Also, it was given that f dash of x is not equal to 0, or sorry, f dash of t is not equal to 0 for every t belonging to I. If that was the situation, then it is important. In some of the problems also you may end up getting this condition that f dash exists and is continuous and never becomes 0. This condition implies that f is strictly increasing or f is strictly decreasing. Why? Because if f dash, suppose why is this true? It's f dash exists and is continuous, but suddenly suppose f dash of t becomes 0, then it is a decreasing function after that. So this situation will never happen, and therefore the function will be either strictly increasing or strictly decreasing, implying that it is 1 1 on 2. And therefore the inverse was possible, and therefore we had set up the composition of the function like this. This was e to f, that was the range of your g, and from a to b it was function f whose range was c to d. And here, because f is monotonically strictly increasing or decreasing, you can always have inverse, f inverse. Okay, and therefore the composition of the function from x to y, basically we want to establish this is x, this is y, and this was t in between. So dy by dx we wanted to find out, and our y was basically g of f inverse of x. So if we want to find out y dash, it would become g dash of f inverse of x into f inverse dash of x, and f inverse of x, f inverse of x is t. Therefore this was g dash of t into f inverse dash of x is 1 upon f dash of x, and therefore we get g dash of t upon f dash of t, which in ratio form we get dy by dx, dy by dt divided by dx by dt. That is how we proved parametric differentiation last night. Okay. However, in parametric differentiation, this condition that f dash must exist and is continuous is a very strong condition, because in many applications you might not get this, that f dash exists and is continuous. So will parametric differentiation fail in that case? That is the question, because the required conditions are not satisfied. But then it is not true that parametric differentiation will not fail, it will continue to work. And who supports or who helps that parametric differentiation to still hold it true is the theorem called Darbus theorem. Darbus theorem will help you to overcome the stringent requirement of f dash of being continuous. That is that even if f dash is not continuous, that is fine. In f dash has intermediate value property. If intermediate value property is there, and even if the function is not continuous, f dash is not continuous, still we can apply our parametric differentiation theorem to that kind of function. So we will understand this little better once we prove this particular theorem, Dharmus theorem. So let me have the statement of Dharmus theorem. Let f be defined from a comma b to r if 1 f dash exists on a comma b, then 2 f dash has a intermediate value property. Now, what does this mean? This means that f dash evaluated at A and f dash evaluated at B, suppose they are two different values. What is the meaning of this? Let me write down. F dash at A and f dash at B, suppose they are distinct values. Without loss of generality, suppose f dash of A is less than f dash of B, then there exists some point C, belonging to A comma B such that f dash at C such that f dash of A is less than f dash of C is less than f dash of B. Suppose f dash of A and f dash of B are not the same values, so there will be many terms between these two. Suppose k is a real number. Suppose f dash of A is less than k is less than f dash of B, then there exists C in the open interval a comma b such that f dash of A k f dash. There exists some C which will, and every time it will happen. For all the values between A and B, there will exist C which will give you the required value k which lies between f dash of A and f dash of B. That is what is the meaning of Dharmus theorem. It has intermediate value property. So basically what we are trying to say is, in the parametric differentiation, f dash exists and is continuous. Okay, f dash exists and is continuous. So this word can be eliminated from this theorem, and if f dash exists, it always has IMVP, and IMVP is good enough for parametric differentiation. That is what Dharmus theorem's significance is. So we need to prove this theorem, Dharmus theorem, and I give you some time for working out the proof, because this is something similar to the intermediate value theorem that we had done, but intermediate value theorem was for function f. This is for f dash, derivative of that function. So there is slight change, which if you incorporate, you will get this Dharmus theorem proof. So I give you some time. Okay, proof. Without loss of generality, let f dash of A be less than f dash of B. Let k belong to R be such that f dash of a is less than k is less than f dash of b. Define g of x is equal to f of x minus k times x. Okay, given f is differentiable, f dash exists, kx is differentiable, as f is differentiable and kx is differentiable, g of x is differentiable over a comma b. Okay, therefore g dash of a is equal to f dash of a minus k, which is now f dash of a minus k is less than 0. G dash of b is equal to f dash of b minus k. F dash of b minus k is greater than 0. बरोबर चालू है. And g is continuous over, g is differentiable over a comma b, and hence it is continuous over a comma b, as g of x is continuous over a comma b. Now here I am going to say that there exists c belonging to a comma b such that g dash of c is equal to 0. Why? Now think about this and tell me, why is this statement true? G of x is continuous over a comma b. So there exists a comma b in the open interval such that g dash of c is equal to 0. Why should it happen?
Because f dash has IMVP.
That is what we have to prove, huh? F dash as IMP. We have to prove f dash as IMP.
Sir, is it because Bolzano stress?
Is it because Bolzano stress? No, Bolzano stress no, because it's a derivative. I mean, we are getting a little bit confused with g of x and g dash of x. This condition is on g dash and it is not on g. If it was straight away, then you are right, Bolzano stress will do your job. But here, what we are using is g of x is continuous over bounded interval a comma b. Therefore, it must attain its bounds. It must attain its bounds. So we can have situations like this, that we have 2 points A and B here. Okay, and suppose f dash of a derivative That means slope of tangent of function at a. F dash of a, not f dash of a. What is this? G dash at a. Suppose g dash at a is negative, and suppose g dash at b is positive. Suppose b is here, and g dash at b is positive. Okay, this is capital A. Point on the curve. If I draw tangent, point on the curve. If I draw tangent, then this statement says g dash of a is less than 0. Therefore, slope is negative. This statement says g dash of b is greater than 0. That means slope is positive. And then we are saying g is continuous over a comma b. Therefore, this is local maximum. This is local maximum. They are attained by the function g of x, and therefore it must attain the local minimum also. Therefore, there is no way for the function to go like this and be like this. I mean, this is the simplest way of drawing this function, and therefore this is what is the minimum of g of x. Okay, this blue curve is g of x. G dash at a is less than. I mean, this is without loss of generality. We can have exactly opposite. But in this case, g dash at a is negative. G dash at b is positive. Therefore, these are local maximums. And as it is a function which is continuous over bounded interval, we have proved the theorem that it is bounded and it attains its bounds. That means the minimum must be attained, and when you attain the minimum and when it is continuous, you have to cross this. G dash of c must be equal to 0. That is what is the local minimum between a and b. It might be present once or it might be present many times. But at least there will be one c between a comma b, which will give you g dash of c is equal to 0. And then it is simple. If g dash of c is equal to 0, g dash of c is equal to 0 is equal to f dash of c minus k is equal to 0 implies f dash of c is equal to 0. Okay, so this is what is the result, and therefore even if f is not continuous, even if f dash is not continuous, it has IMVP, and because of this property we are allowed to use our previous theorem. Now let me give you one example of a function where a derivative exists but is not continuous. Derivative is not continuous. So if we take one example, might be we are little better as far as understanding of Dharmus theorem is concerned. So example, example is our friend f of x is equal to x square sine 1 upon x. If x is not equal to 0, is equal to 0 if x is equal to 0. Now find out f dash of x. Find f dash of x of this function and check its continuity. Okay, so this function f dash exists. You will find that f dash exists, but continuity is not available of f dash. F dash, find f dash and check its continuity. Continuity of f dash you have to check. Okay, and therefore, but then this function has all IMVP. Whatever value you want is available at some point C somewhere because it is oscillating function. So what is the job in hand as far as you are concerned? find f dash of x and check its continuity. What is the derivative of f of x?
2x sine 1 upon x minus cos 1x.
F dash of x is equal to 2x sine 1 upon x minus cos 1 upon x. Is that right? That x square business will get cancelled. Now, this is going to be oscillating and therefore 0, I mean if x is not equal to 0, if x is equal to 0, therefore if you observe the continuity of this function not continuous at 0. Okay, but then as per Dharmus theorem, even if it is not continuous at 0, it attains the intermediate values. No matter what interval you consider, it attains all the intermediate values. F dash has intermediate value properties. And the basic trick of that, why it works, is because if a function is continuous over closed and bounded interval, then it attains its bounds. Then it is bounded and it attains its bounds. That was the basic theorem which we did. Properties of continuous functions, which helped us to get the IMVP property. Now, if IMVP property or f dash is available, then parametric differentiation is also possible. This is what is the fact, and you need not have to have the continuity condition for parametric differentiation. You can still go ahead and do the derivative in this fashion. dy by dx is equal to dy by dt upon dx by dt will still hold true. I mean, we will restrict our discussion as far as this implicit or parametric differentiation is concerned at this stage. And if one wants to study it still deeper, literature is always available on the internet. Okay, so now let us move on to the next and yet important theorem. When we learned Jensen's inequality sometime in 9th standard, I think, we did at that time defined the convex. What do we mean by convex function? So let me draw and you tell me. I mean, if a function looks like this, let me have it 56%. Okay, if the function is looking like this, we call it as convex. If the function is looking like this, we call it as concave. Okay, and there could be many different functions looking other than this. That is fine. Essentially, if you remember, we said, we need a mathematical definition of a convex function, because drawing a sketch and saying that this is convex is not acceptable. So you take 2 points on that function, say a and b, and find out values of the function f of a, f of b. Okay, then we are saying if you join this, then this is a chord passing through capital A, capital B, chord AB. If for any value of x between a and b, if you evaluate the function, value of the function, and if you evaluate the value on the chord, so suppose, I don't know why it is, okay, so suppose this is the point, say C. If I am evaluating this point for a value of on y-axis, this will be f of C, because this curve is f of y is equal to f of x. And then if I want to find out what is the y value of this, then I have to use the section formula to get this y. I mean, do you recollect whatever we have said at that time? So, definition. Let us write. At that time also I had told you that we will revisit this when we learn differential calculus and write it again. So, definition. Let f be defined from I to R. F is said to be convex. If convex on I, if and only if for every x1 comma x2 belonging to I, x1 less than x2, and for every lambda 1 comma lambda 2 greater than equal to 0 and lambda 1 plus lambda 2 is equal to 1, we have f of lambda 1 x1 plus lambda 2 x2 is less than or equal to lambda 1 f of x1 plus lambda 2 f of x2. So typically if you see, this is section formula. So this is point on chord and this is point on curve. It is as simple as that. So converting your geometry, understanding of geometry, what we call a convex curve, into the mathematical definition. Chord above or chord below the curve. If chord is above the curve, convex. If chord below the curve, concave. So similarly, f is said to be concave on I. Just complete this definition part. Then for everything, this statement will remain as it is. The inequality will flip. F of lambda 1 x1 plus lambda 2 x2 is greater than or equal to lambda 1 f of x1 plus lambda 2 f of x2. Okay. So if this is the curve which is convex, this is f of x, and below that if I try to plot the f dash, this is f of x. If I try to plot f dash of x below that, then slope is negative, very high, very negative. Negative in becoming little positive, it becomes 0, and then again it becomes positive. So this is my x-axis. Okay, so f dash will look like this, and if I plot f double dash, f double dash means what do I do here? It is a positive slope, positive slope, positive slope. Slope becomes 0 and still again it becomes positive. Okay. Is this going to be horizontal here or it is? No. No. Mistake. f dash is going to be something like this, right? And if f double dash, if I want to find out f double dash, then slope is going to be continuously positive. At any point, f double dash of x is going to be, I mean, mx, it's going to be a big positive number, then small positive number, then small positive number, and again big positive number, something like that. So f double dash of x is greater than or equal to 0. F double dash of x can be greater than or equal to 0. That is what as far as f double dash is. So what am I trying to do here is theorem, if f double dash of x is greater than equal to 0, then sorry, आता मला greater than equal to 0 मिळाला. Greater than equal to 0, then f is convex on I. And if f double dash of x is less than or equal to 0, then f is concave on I. And of course, f double dash exists. So prerequisite, let me write down prerequisite. Let f be the function defined from I to R. Let f double dash of x exists on I. If that happens, so can we say that if f double dash of x is greater than 0 or equal to 0, then it is convex? At least whatever drawing work which we have done here, yes, seems to be true. But that is not acceptable. We cannot prove theorems by sketching the curve. We have to write the algebraic proof. I give you some time to try your level best. What is given? F double dash of x is greater than 0 or equal to 0 for every x in that interval. Okay, let me give you the setup. Now it is given that f double dash exists on I, and let us take this case where we want to prove it to be convex. Similar work if we do for the second, we will be able to show that it is concave. Okay, so let x1 comma x2 belong to I. Let x1 be less than x2. Let lambda 1 comma lambda 2 belong to real numbers. Let lambda 1 plus lambda 2 is equal to 1. Let lambda 1 comma lambda 2 be greater than 0. So geometrically, if we have x1 here, x2 here, and x here, then we can say lambda 2 is to lambda 1. Then by section formula, can we write down x lambda 2 x2 essentially what we have is x minus x1 upon x2 minus x1 is equal to lambda 2 upon lambda 1. This is the fact that we ठीक है. Okay, so this is the setup, and what at is what you have to eventually arrive at is this statement, this statement. You have to arrive at this, and algebraically it should be possible. Of course, you have to use the given condition. If double dash of x is greater than equal to 0 implies something that you need to use. So, almost I have opened up everything. Now it is only question of writing the details and finishing the proof. Okay, the key to this proof, simplistic proof, Pranav has done it some other way, but conventional way of proving this is applying ambiguity. To say x1 comma x, what will we get? F of x1 minus f of x upon x1 minus x is equal to f dash of c1, where x1 is less than c1 is less than x. Applying LMVT to x comma x2, we have f of x minus f of x2 divided by x minus x2 is equal to f dash of c2, where x is less than c2 is less than x2. So this is simple application of LMVT. So we are getting these two results, 1, 2. Now here we would like to use the condition f double dash of x as f double dash of x greater than equal to 0 implies f dash is so if f double dash is greater than equal to 0, that means f dash is increasing function. Is that right? And therefore this implies f dash of c1 is going to be less than f dash of c2. Is that correct? This implies f of x1 minus f of x upon x1 minus x is less than or less than we can allow equality because equality over here is available, therefore we can have equality here also, because if it is a constant function then we will include it in convex as well as concave. So everywhere equality, therefore c1 is something like this is less than or equal to f of x minus f of x2 upon x minus x2. Okay, बरोबर चाललंय, बहुतेक चाललंय ते बरोबर चाललंय. पुढे आता इथून पुढे सिम्प्लिफिकेशन, आता काय करूया, क्रॉस मल्टिप्लाय. you get. आता क्रॉस मल्टिप्लाइंग करताना x1 minus x is negative. काय बरोबर आहे का? काय काळजी घ्यायला पाहिजे आपल्याला आता इथे? Shall we make them positive? This implies f of x minus f of x1 upon x1 minus x is less than or equal to f of x2 minus f of x upon x. We have to change this also now. X minus x1, and then this will be x2 minus. So we are playing safe. Now the ratio that we already have, where lambda 1 and lambda 2 will come in picture, is x upon x1 divided by x2 minus x. दोन्हीकडे मी चुकीचं लिहिलेलं आहे. x minus x1 upon x2 minus x2 minus x, and therefore this implies f of x minus f of x1 is less than or equal to x minus x1 upon x2 minus x f of x2 minus f of x. This implies f of x minus f of x1 is less than or equal to, what is this, lambda 2 upon lambda 1 times f of x2 minus f of x. Okay, so further this implies cross multiplying. Now lambda 1 and lambda 2 are greater than 0. Therefore lambda 1 times f of x minus lambda 1 times f of x1 is less than or equal to lambda 2 times f of x2 minus lambda 2 times f of x. So we have to collect f of x towards one side, which is lambda 1 plus lambda 2 times f of x is less than or equal to lambda 1 times f of x1 plus lambda 2 times f of x2. This is equal to 1, which implies f of, and how do we write f? How do we write x by section formula? Lambda 1 x1 plus lambda 2 x2. If we simplify that ratio, we get this is less than or equal to, this point on the curve is having smaller value than point on the chord. Hence convex by definition. Okay, so I just keep everything on board, you copy it, and then we move on to the next. Here I can say, if we simplify this, what we will get, x is equal to lambda 1 x1 plus lambda 2 x2. Now, question, what is your intuitive answer for, hello, share, what is your intuitive answer for converse? Is converse true? Is converse true? What will be the statement of the converse? If the function is convex on I, then f double dash of x is greater than equal to 0. Okay, think about it. First of all, intuitively, what do you think? Will it be true or false? And then depending on that, we will decide whether to search for counterexample or whether to go for writing proof. Okay, intuitive answer for this is the converse is true. Yes, converse is true. Let us do some efforts to get the converse also in place. एवढं मोठं झालं हे. बरं.
But what if we can define a function that is convex but not differentiable or not double differentiable?
नहीं समझा. If the function is convex and
So is there no function that is convex but it's not double differentiable?
no, I mean, see, when I'm asking a short statement like this, f double dash of x exists. We are going to consider the functions where f double dash of x exists, because if f double dash of x I cannot find out, then there is no question of checking whether it is convex or not. So when we are saying that function is convex on I, we mean if I take 2 points in that interval and join the chord, then point on the chord is above point on the curve re x1 comma x2 in that interval. That is what is implicit when I say f is convex on I. Okay, and then what you are trying to tell me is if the function is not differentiable, then we will be in trouble. So, okay, so basically what we are trying to do here is we are assuming that function is well behaved, f dash is available on I, f double dash is also available on, and it is greater than equal to 0. Can we prove that it is greater than equal to 0 if the function is convex in nature? That is what is given. So we are not going to consider a function maybe like this. I mean, what you have in mind, Pranav, is something like this. This is not the differentiable function. We have to define in pieces, right? You are right. I mean, it should have been given that the function is not like this. Here it is not going to be differentiable at these points. So there is no question of double derivative. But if it is well behaved function looking like this, then yes, this is going to be true. Let us begin. For that we need to prove 2 lemmas. Lemma 1. Let f be defined from open interval a minus delta to a plus delta to r. F dash of a exists. Then limit h tends to 0, f of a plus h minus f of a minus h upon 2h is equal to f dash of a. This is the first statement of the lemma 1, and it is easy to prove. Please prove. Easy, because a small adjustment and you are there. This implies limit h tends to 0, f of a plus h minus f of a plus f of a minus f of a minus h upon h into half is equal to is equal to what? You can take that half is outside, half of limit, that is f dash of a plus f dash of a is equal to f dash of a. Lemma number 2. Let f be defined from a minus delta to a plus delta to r. F dash exists on a minus delta to a plus delta. F double dash exists at a. Then limit h tends to 0, f of a plus h plus f of a minus h minus 2f of a upon h square is equal to f double dash of a. Prove it. Applying L'Hopital, we get. Applying L'Hopital, we get limit h tends to 0, f dash of a plus h plus की minus बोला derivative part है ना with respect to h you are differentiating, therefore it should be minus in between f of a minus h, f dash of a minus h, and this is constant, so 1 divided by 2h. Oh, but this is same as lemma 1 equal to f double dash of a by lemma 1. Okay, so these two lemmas are there to help us out. Now let us do the setup. What is being given to us? We have
Share the screen.
that we have got the information about the function. Given function f is convex. So by definition, f of chord f of lambda 1 plus lambda 2h2 is less than or equal to, point on the curve is smaller than or equal to point on the chord. Okay, this is given to us. This is given to us. Now setup. Choose x1 is equal to x minus h. x2 is equal to x plus h. Lambda 1 is equal to lambda 2 is equal to half. Simplistic. We can create complications here and still we can prove the theorem. But if we keep it simple, it will be easy for us to prove. Therefore, f of lambda 1 is half, x1 is x minus h. So f of x minus h upon 2 plus x plus h upon 2. This is LHS. This is given to be less than half common inside bracket f of x minus h plus f of x plus h. Are you there? Somebody is going out, somebody is coming in, going on. Okay, so this is there. So what we can is this implies, now if we just split everything, we get f of x is less than or equal to I can get this to this side. Okay, this implies f of x minus h plus f of x plus h minus 2 f of x is going to be greater than equal to 0. And if I divide this by h square, dividing by h square, as h square is greater than 0, I am not changing anything, and therefore I get a situation f of x minus h plus f of x plus h minus 2 f of x upon h square is greater than equal to 0. And if I apply lemma 2, applying lemma 2, what we get is f double dash of x as extends to f double dash of x is greater than or equal to 0. That is what is the finding of lemma 2. Is that right? So we have proved converse. Converse is proved. Any questions you can ask now if you have not understood any step? Little long, but it is okay. We get a wonderful result. F double dash of x is greater than equal to 0. Function is convex. Function is convex. Then f double dash of x is greater than or equal to 0. Solve following problem. Let A belong to R. And is from R to R. Be given by f of x is equal to x raised to 5 minus 5x plus a. Then I think I will take more time to write the problem than you saw. F of x has 3 real roots. If a is greater than 4. Option A. Option B. F of x has only one real root. If a is greater than 4. C. F of x has 3 real roots. If a is less than minus 4. 3 real roots. If minus 4 is less than a is less than multiple choice correct question. More than one answer correct. Okay, we will solve this problem in the next lecture. Okay, you try your correct answer for this is B and D. But how to go about it, we will discuss in the next lecture. Thank you.